When Newton was thinking about his theory of gravity, he did not want it to be a simple explanation. Rather, he wanted it to be a precise mathematical equation kind of explanation which would probably describe gravitational force. Later, he reasoned that inverse square law will do the work. Welcome to the video. In this video, we are going to study about inverse square law for the intensity of gamma radiations. I will be going through the apparatus we can use, procedure we need to follow, and the analysis part which proves this law. Inverse square law. Even before trying to understand this law, let us try to look at a very small example. Take a bottle of paint, try to coat it on a wall. Up close, paint quickly coats. If you are painting it from far away, now it is spread out and it is very less concentrated. You double the distance and you have 4 times the area to cover. You triple the distance, you have 9 times the area to cover. What we are looking at here is called inverse square law, which follows the relation 1 divided by d squared is directly proportional to intensity. Let us try to understand it in a more science perspective. The inverse square law states that for a point source of radiation that is capable of radiating omnidirectionally with no obstructions, the intensity I decreases with the square of the distance from the source. As per this law, let us take a very small example. In source S, we will keep a light. Light loses its brightness or luminosity as it moves away from the source. For example, when you switch on the light in one corner of the room and when you move away from the source, light appears dim or less. It is due to inverse square law. Inverse square law, gamma rays. Inverse square law for gamma rays. In this experiment, we are trying to verify the inverse square law for the intensity of gamma rays. Apparatus we are going to use is GM counting system, Geiger-Müller counting system, GM detector with connecting cables, a gamma source, GM detector holder. What we see here is GM counting system, Geiger-Müller counting system. This is the main apparatus we use in this experiment. It is a device used for detecting and measuring ionizing radiations. It is an instrument that uses the principle of gas ionization to detect and measure the radiation. Geiger-Müller tube. This is a tube connected to GM counter. It is used for detection of gamma radiations, X-rays, alpha, beta rays. It can also be adapted to detect neutrons. What we are seeing here is radioactive sources. You can see the element name on that. There are 2 types of sources in our lab. One is beta source, one is gamma source. How to identify that is very easy. Gamma source are completely enclosed, just like this. Beta source have an opening, a red color kind of thing on one side. This is source holder, where we are going to place our source and place it in GM tube. Now for this experiment we are going to use gamma source. This is how it will be placed in on source holder. GM counter works by using a gas filled tube which you can see there. It contains a small amount of gas, usually helium, neon or argon at low pressure. The tube has a thin wire running down its center and a high voltage is applied between the wire. When ionizing radiation passes through the tube, it ionizes the gas atoms, producing positively charged ions and electrons. These ions and electrons are then accelerated by the electric field towards the wire producing an electric pulse that is detected by the counter, and later we get to know the number of radiations being emitted from a source. Now for this experiment we need to keep varying the distance of the source from GM tube. For that we need to first measure the distance between each slot. In this apparatus it is 0.5 centimeter. In GM counter there are a lot of things you need to preset before performing this experiment. You need to power it on here. Later change the voltage using this knob which is there here. This is where it is going to display all the data about voltage, about time you want to preset, about number of radiations and so on. This is how it is going to look when you start GM counting system. Now here you can see that on the right in the screen we have HV, that is voltage specification. On your left side there is preset time. We can preset time using this program button which is there here. On the complete right we can see a symbol in that display. It means that counting is still going on. Here preset time is 60 seconds. PT is preset time and it is telling it in seconds, 60 seconds. On your right, complete right in the display, we have a symbol. It will be blinking while it is counting the number of radiations. So while it is blinking, it is actually doing a trial. Next, PT is preset time. It is for 60 seconds. ET will tell you how many seconds have been completed since this counting has started. Now it is just 7 seconds. For my lab, for this experiment, operating voltage which I have set is 420 volts. Preset time was 60 seconds. Source which I took was cesium. Even before performing this experiment, without source, we need to calculate the background count, background radiations which would affect our experiment. So there are 24 number of background radiations. After taking a raw number of radiations, we can correct the count. In the observation table, we have distance. First we start with 1.5 centimeter. I've already said that each slot is 0.5 centimeter. Just keep on changing the slot from 1, 2, 3, 4 and keep on increasing the distance between the source and the tube. After keeping the source in GM detector, you can start. Then it will show you the readings, number of radiations count. Now count which I have received here for each trial is, for 1.5 centimeter it is 1037, for 4 centimeter it is 440. First thing you can observe here is that as distance is increasing, count is gradually decreasing, and later get the value for 1 second, which is net count rate in 1 second, that is R. Later we need to get product C, which is equals to R into D square. Here D is distance, R is net count rate. Let us look at these graphs and try to understand what this experiment has to tell. First graph is net count rate versus distance. The graph of net count rate versus distance shows a decreasing trend, implying that inverse proportionality of R versus D. You can see that now at 2 centimeter, let us consider 2 centimeter. At 2 centimeter, the number of radiations is somewhere up to 17. But as distance is increasing, at 3 centimeters from detector tube, it is 12 number of radiations. At 4 centimeter, it is somewhere around 7 number of radiations. When it is at 6 centimeter, it is at 5 number of radiations or less than 5. This is telling you that as the distance is increasing, the number of radiations is gradually decreasing. Looking at the next graph, R versus inverse square of distance. The graph of R versus inverse square of distance shows linearly increasing trend. Here we can see a linearly increasing trend. These are the points plotted and this is the regression line. This implies that direct proportionality of R and 1 by D square. Next graph, log R versus log D. This shows linearly increasing trend which implies inverse proportionality of R and D. Hence, it is found that intensity of gamma radiations fall inversely as square of distance. Hence, the inverse square law for the intensity of gamma radiations is verified. Thank you.